Welcome to the lecture for section 14.5. This is the last lecture video for MGF 1106 Liberal Arts Math, and my name is Jorge. So for this particular section, we have three objectives. And the first thing is that we're going to be talking about linear correlation. So the objectives are that we're going to be able to construct a scatter plot to show the relationship between two variables. And then we're going to understand the properties of the linear correlation coefficient. And then we're going to use linear regression to find a line of best fit for a set of data points. So the first thing is, let's talk about a scatter plot. And a scatter plot is used to determine whether there is a correlation or a relationship between two variables. And the first thing we have to do is we have to obtain the data, and the data will be in pairs. And these are what we call data points. And then what we're going to try to do is relate the first variable to the second variable. Now, to understand such data, we're going to go ahead and plot what we call a scatter plot. So let's look at an example. So here we have an example. An instructor wants to know whether there's a correlation between the number of times the students attended tutoring sessions during the semester and their grades on the 50-point examination. So the table shows the data for 10 students. Now we're going to go ahead and represent these data points by a scatter plot, and then we're going to go ahead and interpret the graph. So here we have our x values, which is the number of tutoring sessions, and then the exam grade that corresponds to each student. Now, what we do is we can plot the points. So we plot the points 1842, 631, 1646, and so on and so on. And these points, again, correlate to this table down here, number of tutoring sessions and exam grade. So as the number of tutoring sessions increases, the grades generally increase also. And you can see that if we were to draw a line, and this is the last section of this lecture, so the line of best fit. If we were to draw a line, we can actually see that the line it's increasing as we go from left to right. The next thing we're going to talk about is linear correlation. And linear correlation exists between two variables if when we graph the points in the graph, they tend to lie in a straight line. Now, the linear correlation coefficient allows us to compute to what degree the points are actually correlated or related to each other along this straight line. So the formula for computing the linear correlation coefficient is as follows. And as you can see, it's a pretty involved formula. So if we have pairs of data for two variables, let's say x and y, then the linear correlation coefficient for these data points denoted by r is given by the following formula. And then again, n is the number of pairs of data that we have for x and y. So let's go ahead and compute the linear correlation for the table that for the example that we did previously. So the first thing is that we begin by creating a table with the necessary components of that formula. And this is this next slide here. So as you can see, we have everything that we need for the formula. So we have the summation of x, the summation of y, the summation of x squared, the summation of y squared, and then the summation of the product of x and y. And those are the values that we're going to need. So when we construct these tables, we're going to need a column for x, column for y, column for x squared, y squared, and then a column for the product of x, y. So now we have these values, which is the last row in this table. And we're going to go ahead and use them in this formula. So here's the formula. So r is equal to, and so we have n times the summation of x, y minus and all the components of this formula. I won't go through them because you guys can read them. And what we do is the values that we have, we just go ahead and substitute them for the variables that we have here in this formula. And then we get that the linear correlation coefficient for this particular data set is approximately 0.9068. Now, what does that tell us? So here's some properties. R is going to be a number that's going to be between -1 and 1. And it could be -1 and it can be 1. Now, if R is 1 or -1, then that means that the scatter plot lies on a straight line. That means that the two variables, in this case x and y, are really essentially they're correlated with one another. So if R is positive, there's a positive correlation between the variables, and essentially means that the line is going to go up from left to right. If R is negative, then there's a negative correlation between the variables, and the line is going to go down from left to right. So if r is close to 1, then there's a significant positive linear correlation between the variables. And the scatter plot is close to line along a straight line that rises from left to right. And again, if r is close to -1, then there's a significant negative linear correlation, and the scatter plot, of course, falls from left to right. Now, if r is close to 0, then there's little or no linear correlation between the variables. So here we have the different types. So the first one is a positive correlation, and that means that whenever x increases or y decreases, then y changes in the same way. And here we can see this line. So this is very close to 1, so it's going to go up. Now, we say that there's a negative correlation between the variables x and y. If whenever x increases or decreases, then y changes in the opposite direction. And this is this one over here. And this is where you can see that there is no relationship between the data points. There's nothing. There's just no relationship there if it's just all over the place. So there has to be some sort of pattern, if you will. And this doesn't have a pattern in it. So we have another example. We're going to go ahead and compute R for the n pairs of data. Now, if the absolute value of R exceeds the number in the column labeled alpha, and alpha here is 0.0 on the line n, then there's less than a 5% chance that the variables do not have a significant linear correlation. If the absolute value of R exceeds the number in the column labeled alpha 0.01 on the line n, then there's less than 1% chance that the variables do not have a significant linear correlation. So here's an example. We wish to determine if there's a relationship between the weight of a car and the gas mileage. So the table shows data regarding gas mileage of cars with various weights. We're going to find the correlation coefficient for these data, and we're going to determine whether there's a linear correlation at the 5% or the 1% level. So here we have the data. So we have weights in hundreds of pounds, and then we have the city miles per gallon. So the first thing that we're going to do is we're going to go ahead and represent the weight by x and the gas mileage by y, and then we find all of the points, all the information that we need to calculate R. So when we draw the table, we calculate our values, and R comes out to be negative 0.8507. Now there are 10 pairs of data. So what we do is we look at line 10 on the table on the previous slide that we had, and then we find the value of 0.765 under the alpha of equals 0.01 column. Now the absolute value of R is 0.85. So we are 99% confident that there is a significant negative linear correlation between car weights and gas mileage. Next thing I want to talk about is what we call the line of best fit. So the line of best fit, essentially what it does, it minimizes the sum of all the vertical distances. Now we wish to find the line that best models our data, and this is what we call the line of best fit. And essentially, again, this is a line that minimizes the sum of all the vertical distances from the data points to the line. Now, here's the definition. Line of best fit for a set of data points in the form of xy is of the form y equals mx plus b, where m is calculated using this formula and b is calculated using the formula that's given. Now, we use what we call linear regression to find the line of best fit. Oops, sorry. So here's an example. Let's go ahead and find the line of best fit for the set of data points below. So again, number of tutoring sessions and an exam grade. So the solution is that we compute n is 10, summation of the products is 4090, summation of the x is 98, summation of the y's is 376, summation of the x squares is 1396, and we're going to go ahead and use that information to find the slope. So m is equal to approximately 0.9302. Now the y-intercept, which is b, is equal to 28.48. So therefore the line of best fit is equal to y is equal to 0.93x plus 28.48. So what happens is that we can actually guess the grade on a student's 50-point examination based on the amount of hours that they went to tutoring. And that's the end of section 14.5. Thank you.